All right, welcome back. Now, let's see here. So we are going to create a linear regression model today and a few more other regression models just to compare them with linear regression. So let's start. For this one, we're going to use data sets. So we're going to start with data sets. And what this will do is it's able to reach online data set resources out there. Okay. Um, The one we're going to use is if you search for import, is this one, import 1985. So let's use that. Okay, if you double click on it, if you see this green circle there, green light, you're good. Let's check it out. All right, so you see there's the price. So this is a target variable. It's highlighted like in this gray color. That's why, we can use regression here, right? It should be the target variable should be a numeric continuous value like this one. And then there is some other measurements for each point here. Each row is a vehicle, you see from this make. There's different vehicles. There's different attributes of those vehicles. There's, for example, city miles per gallon they do, highway miles per gallon they do, and some other measurements here. Some of these are numeric, some of them are categorical. Now, here let's do there. Okay, data info. Let's have a quick look at this. Okay, 205 rows, 26 columns, 11 categorical, 14 numeric columns. The target variable is a numeric type. There's 55 points missing in total, and 4 of them are in the target column. Okay, so for now, we are not going to do anything with the missing values. When we just build a model, it will be um, eliminated there. Okay, but in the future, we'll look into some other methods there. Now, one thing here, when we select the data, that's it. We can't do any changes here. For example, we cannot change the target variable or anything like that. So if you search for edit domain, this will come up and this will help you see what type of variables you have. And if it is a categorical type, how many unique values there are. For example, the symboling is a categorical type and these are the values in there. Normalized loss is a numeric type and nothing is shown there. This body style, for example, it's categorical and these are the values there. Some of these might be wrong, you never know, so it's better to check and make sure everything is good. So for me, it looks good. Okay. Now, there is a widget called Select Columns. This one, here you can see what this will do is will help you to select some of the features if you want to not use all of them. By default, the target variable is selected and everything else is being used in the model, okay? So with the select columns, first of all, one thing you can do is change this target variable if you wanted to do so. For example, let's say I don't want to use the price, but I'd rather use this city miles per gallon. Maybe that's my goal. If I want to predict how many miles per gallon each car is making in the city, I can use that as input. And for now, if let's say if I don't want to use price at all, I can keep it here. This is the ignored area. This means it's not being used. After the select columns, if I continue to build a model, those columns here will not be used. Or I can just put this back here, etc. So I can make changes like this. Okay, but um, okay, let me delete this. This is not what I wanted to show. Um, I don't want to make any changes. Basically, that's what I'm trying to say. I just wanted to see that indeed the target variable, oh, because I made the change now it's sticking there. So I need to put this back in. So let's put this back in. You go up there, price, you come here, and then you go into my target variable. Okay, yeah, we want to predict the price of the vehicle. So let's keep it there at the target area and everything else as input. Okay, let's keep it like this. This we are maybe in the future we'll use this, but for now we are not going to use it. I just wanted to see and make sure it's like that. where the price is the target variable. Okay, now let's create a linear regression model. Put the linear regression right there and make a connection. The linear regression model already is trained now. I can see the coefficients by doing this. Yeah, you see it says coefficients data. Yes, please. So this will show the coefficients in this table. Now what do we see here? We see the coefficients, beta 0, beta 1, beta 2 values. All of those coefficients for each of the variables are shown here. There's a lot. Now one thing, if you pay attention, is this one. This one is very obvious. Let's look at this one. The car types, manufacturers, Alfa Romeo, Audi, BMW, etc. They are all separated out. You see they have their own beta value, beta coefficient. But in the data set, right, this is our data, that was just a single column right there. You see, that was just a single column with the different vehicle manufacturers listed there. That's it. So why do we have a lot of new columns here in the coefficients? Well, that's because what's happening here is one-hot encoding. Okay, orange applies one-hot encoding. It doesn't apply dummy variable. It applies one-hot encoding because you see symboling was a categorical type with values 0, 1, 2, 3, and -1 and -2. And this edit domain will help you in terms of seeing how many unique values there are in that variable. You see symboling, the unique values are 0, 1, 2, 3, -1 and -2. So they are all listed. If you see the coefficients for each one of them, that means they're all present as new columns in this linear regression model, and that means one-hot encoding was applied. Why is this happening? Well, because first of all, categorical types or text types cannot be used directly in a machine learning model. So they have to be converted into numeric value. So that's why this binarization happens. It is 0 when that value in that row is not present, and it is 1 when it is present. Okay. So I will show you in this one. Let's say this row is for the make, right? And let's say we have BMW, we have Audi here, we have another BMW. I don't know, we have Honda, we have another Honda, and then we have a Toyota right there. Okay, so what does one-hot encoding do? Let me put this in the corner so it looks better. Well, the unique values will have one column now for themselves. So this will be, generally it will be coded like this, make and then BMW. And then make Audi will have its own column. We have make Honda, and then we have make Toyota. Okay, let me make this bigger too. Where is this one? This one. Okay, so what does this mean? Well, the model cannot use this column because this is not numeric, first of all. Even if it was encoded in numeric way, meaning instead of names like this, if you were to see 0, 1, 2, 3, 4, 5, 6, etc. for each of the corresponding make, that doesn't mean it's numeric type yet. It's still a categorical type. Okay, so you still have to convert it into a proper numeric format, and that's what this will do. This is one-hot encoding. So where that value is present in that row, it will have a 1 in the corresponding column of it. So this will be a 1, and the rest will be 0. You see, 1, 0, 0. So the name comes from here, one-hot. Only one of them is 1 in that row, and the others are 0. Audi, well, the BMW column will be 0 for Audi. Audi column will be 1 because it's an Audi. Honda will be 0, Toyota will be 0. BMW, so you see BMW right there, that's a 1. Audi will be 0, Honda will be 0, Toyota will be 0. So Honda, BMW is 0, right? Honda, Audi, it's 0. Honda. Now that's a 1 right there. Toyota, that's a 0. So 0, 0, 1 because Honda is in this row, right, for this column, and the rest is 0. Toyota 0, 0, 0, and this will be 1. Okay, this is what one-hot encoding does. Now, after this conversion, there's a 0 right there. After this conversion, this column is deleted. This is not used anymore, that column. It cannot be used anyway, but basically it's, it's implicitly kind of deleted such that it's not used in the model anymore. Now we are left with this. So you see we had one column before, now we have four new columns. Now this is one-hot encoding. Dummy variable is very similar to this idea. It is basically one of these are randomly selected, generally the first one maybe, and that's the reference column. So that's being dropped. Okay, I will, let's do this. Let's come here. Okay, that's the reference column. That's not being used. Only these three columns are left. And you see that we had BMW there. So BMW is going to be represented when other cars are all zero. So you see if it is not a Toyota, not a Honda, not an Audi, it's all 000, then it must be a BMW because we only have four options based on our data set. So that's how it is. So that's the reference column. So everything else is zero, then it's a BMW. Okay, so that's how it works in dummy variable. And the main reason for this is because in order to find in statistical method in the traditional way to find the coefficients in linear regression, the inverse of the matrix is calculated and then there, matrix multiplications take place. In order to calculate the inverse of a matrix, you have to have none of the data columns should be redundant. Right now, this column, this BMW column, is redundant because it can be found out from the values based on other columns here, right? Because if this is 000, then I know there's a 1 right there. So it's redundant. I don't need it. It's extra information, kind of. So because of that, the matrix cannot be inverted, and then based on that, the coefficients cannot be calculated properly in linear regression the way it is done in the classical method, the statistical calculation, basically. But there's other methodologies as well to calculate the coefficients, which do not apply directly that coefficient, the inverse, but rather apply, for example, kind of the like a gradient descent method, for example, to find to minimize the error between the predictions and the actual values. And it's an iterative method, right? So by applying that method, it will try to over time, basically after several, maybe 100 iterations or whatever, it will try to reduce its error as much as possible. And at the end, these two solutions will meet at the same point. Okay, they will meet at the same point or very close. They will be very close to each other. So meaning either using the gradient descent method to calculate those coefficients or using the classical matrix inverse method. At the end, I mean, you might have to do lots of iterations, maybe thousands, maybe millions in some case to get to the same point, but eventually they will meet at the same point. But basically in that method, one-hot encoding is fine. So you do not have the dummy variable encoding, okay? So I think here I'm assuming that the Orange also does that, so that's why they are applying this one-hot encoding. All right. Okay. So, okay, that's that. This is important. So I hope it's clear now. You see we have all these coefficients now, and because we have so many categorical variables and we have so many unique values within the categorical variables, we end up with 81 columns now. That's quite a bit. Okay, but now our data is ready. I mean, our linear regression model is ready. We can see the coefficients. Now, one thing, there is no, as far as I know, in Orange, we cannot see like the p-values of these coefficients, like how significant they are. We cannot see those kind of information. Just letting you know on that. Now, okay, what else can we do? Well, let's see. Let's take out from a linear regression, and you see we have predictions there. So you can search for predictions, and this will make predictions. So here, when you double click on it, you won't see anything. And the reason is this. This line connects the model to the predictions, but where is the data? So basically predictions is saying, okay, thank you for giving me the model. Now give me the data as well, the input data, such that I can take that and by using your model, I can make predictions. Okay, that's what it is saying. So it expects us to provide this input as well from the data. And now we see the results. If you see something like this, there's a warning there. So basically it says instances with missing targets are ignored. Remember there was like 4 rows with missing target values. It basically drops them right away and then makes predictions for the other ones. This is the prediction column. This is the actual value. The difference between them is the error. You see there 15,000 minus 13,500 or so is 1,700. So that's the error we are making. That's the difference basically. You can order these columns from small to large, or order the error column as well from small to large or large to small. And you see for the price where it's missing, it didn't make any predictions for those. Okay, perfect. What else? Now let's see the performance of our model. Okay, I think, yeah, at the bottom of this predictions, you can see the scores as well. But what we will do actually is get an output from linear regression and write test and score here and add that widget. So we are going to create a scoring. Now the same idea as well. If I double click on it, it will be empty because again, the same idea. Okay, thank you for giving me the model. Okay, test and score is saying thank you to the linear regression, but now it expects the data as well. It's saying, okay, where am I going to make predictions on such that I can measure the performance of this model? The data is coming from here, so let's connect that. When you double click on it, so this warning is the same, those 4 rows are dropped, which is fine. You see the metric here. That's the R-squared value. We have some other measurements as well for linear regression or for regression in general. Mean squared error, root mean squared error, mean absolute error, and mean absolute percentage error. Okay, that's all there. And you see this result is not bad. Now, a few things I need to explain here. What are these? Well, you see random sampling is basically, give me 1 second here, guys. I will search for, I want to show you a picture. I want to show you a picture of the cross-validation right there. Let's start with that. Okay, wait. Can I get this a full-size picture here? Yeah, that's much better. Okay, so one way to handle this is going to be to do cross-validation. Okay, what cross-validation does, I want to find another one. Yeah, this should be simple enough, yeah. Okay, let's use this one. Okay, so what does cross-validation mean? We take the data, okay, and then we split it into equal sized folds. Okay, if you do 5-fold cross-validation, that means you will split your data into 5 equal portions. That's fold number 1, 2, 3, and 4. Okay, those are the splits here. And now at each iteration, we are going to take one of the fold for testing and 4 others will be used for the training the model. Okay, so here in the first run, this fold number 1 is going to be used for testing to measure the performance of the model. Fold number 2, 3, 4, 5 is going to be used for training of the model. This means that this portion here, this 2, 3, 4, 5, the model basically learns from that data such that it learns those beta coefficients. And after that process is done, the model makes predictions on this fold number 1, and then the predictions from fold number 1 will be compared with the actual labels of fold number 1, such that the difference can be calculated, and then those measures can be, obtained, right? That's how it is. The measures, by measures, I mean these ones, the mean squared error, root mean squared error, all of these are squared. Everything is basically, at the end, it's based on the error, meaning the difference between the actual and the prediction values. So by doing this method, okay, and then basically in the next iteration, we will go to fold number 2. So fold number 2 now is our test. Number 1, 3, 4, 5 together will be our training set. And we will repeat this for 5 times, right? We will go to fold number 3, 4, and 5 like this. Okay. And at the end, we will have a score for each one, and then we'll take the average. Okay. By doing this, we basically increase the reliability of the model. Okay. Because we are kind of creating like 5 different data sets here. And each time we're training on a different training set and a different test set. So the main purpose here is to make the model more robust, meaning more generalizable, meaning when new data comes in, how will the model behave? That's what I'm trying to learn. Okay, that's the main goal of machine learning in general. This is 5-fold cross-validation. So you can do 3-fold. So then you will have 3 folds. You can do 10-fold. 10-fold is very popular. Or you can do more. If you have large data sets, the more folds you have, the slower it will get. So you need to be careful on that. But basically that's the idea there. Okay, so that's cross-validation. Let's select that. So you see that's cross-validation score. Random sampling is very easy. So the same, very similar to this. Let's say you select 80% here for training. That means randomly, take all of your data, randomly put 80% in training, put 20% in testing. Learn, the model learns from the training portion, and then the model makes predictions on the testing portion, and then those predictions on the testing portion is being compared with the actual labels, and then those metrics are calculated there. And then this is repeated 10 times. You see repeat train test, it says 10 times. And then the average of those 10 results are taken and then they are shown here. So you can, again, change this too. You can make it lower, you can make it more. If I do 100, for example, it might take a bit more time. You see it's much slower because it runs it 100 times. The more runs you have, of course, because there's so many different runs now, the more reliable this output is that you see here. But again, that really depends on how much time you have and how big the data set is. The data here is very small, it's 200 points. So yes, you can do even 100 times, but if it is a reasonable data set with 10,000, 50,000, 100,000 points, I think even 10 or 5, maybe even 3 should be enough there. Test on train data, this one is the one that you should not do. This means train the model on a data set and then use that same data to make predictions on as well, to make, the same data that was used for training of the model is also used for testing the performance of the model. This is like cheating. You should not do this because the model sees and learns from the same data set, and then later on it basically makes predictions on the same data set. There can be memorization going on there, rather than learning. And this can happen. This is called overfitting in machine learning. So then the model will probably give you a very good result because it has already seen the data in the past, but then this is not a reliable output. And you see that here in action. When we do the test on train data, we're getting 96% in R squared, 0.96. But when we do cross-validation, for example, we're getting 0.87. This 0.87 is the one I would take, not this 96 from test on train data. That's not, you should not rely on this. This is wrong. This is like, a teacher giving you exam questions, 10 of them, and then in the exam they ask the exact same questions and everything is the same, the values, the numbers, the questions. So basically, if you knew that if beforehand, right, then you don't need to learn anything really. You don't need to read a book. You don't need to do anything. You just can sit one day before, memorize the question and the solution or the answer. That's it. Then you can get 100 from the exam. But this doesn't mean that you learn anything from it. So it's like that. This test on train data is like that. So don't do that. So what is leave one out? That's the final thing I want to show here. Leave one out is same as cross-validation. Basically, it's the extreme cross-validation case where only a single point is used for testing. All the other points, everything else is for training. Okay, and then it repeats. Basically, it goes through each of these one by one. So each of the points will one by one become the testing point. So basically, it's like cross-validation, right? It's the same idea. But basically, the number of faults is basically the number of points you have. So if you have a 100-point data set, you will repeat this process 100 times because at each time one of the points in your data will become the testing and then the other 99 points will be used for training. This is the extreme scenario. Um, the places where this could be useful is when you have very small data set. Okay, very specific cases like you have only 40 points, 50 points, maybe less than 100 points or so. um, like in areas like biology, medicine, I don't know, things like this, where maybe real human subjects are being used for some experiments or for some testing, like lab um, testing or whatever, then you will not have large data sets. In those situations, leave one out is used quite a bit because they want to use the data in maximum efficiency, right? You cannot just um, you have to be very, very careful there to use the data as good as possible, as much as possible. Basically, that's the idea. All right, guys. So based on this, if you had to choose one, I would go with cross-validation. Random sampling is okay as well. Generally, cross-validation is used out there. Either is fine, I would say. Our model is 87.87 for R squared, so not bad. It's doing pretty good. It's doing pretty good. Okay, let's close this. Now, as a final closing, I would like to add some. Basically, okay, linear regression is this. Pretty much. Now, actually, I would like to do this. So, yeah, let's do that. So when I click this linear regression, um, you see there's a few more things here that we can look into. There is the one we applied that has no regularization. Regularization is like a penalty you apply based on the coefficient value. So it's a penalty that's being added into the error calculation. And that penalty basically, it's like a coefficient or some value um, like that alpha value, for example, that's being multiplied by the coefficient values and it's being added to the error function. So that means if you have larger coefficients, um, that means your error will go up. So that's the penalty there that's being applied. And we do not want larger coefficients because larger coefficients generally mean there's a overfitting happening. We want to prevent overfitting. Okay, that's the main purpose of this regularization that you see here. Overfitting, we do not want that to happen. Overfitting is basically memorization. The model stops learning and starts memorizing the data, so we don't want that to happen. So here we do not apply in regularization. This is by default how it is in general. So that's why I'm going to do this. I'm going to add more linear regression models here. Um, I'm going to delete this predictions. I don't want to make predictions for now. Okay. So I want to make a nice connection here. Um, let's say I want to see the what's it called, the coefficients as well. I just want to make these connections here. Okay. And then what I will do is I want to test and score these models, but I will change those parameters there in the models. Okay. So here I will right click, rename. So this is linear regression. No regularization. This one, I will change this regularization into ridge regression. So that's a type of penalty there. I'm giving these names so that I know which one is which one. This one I'm going to apply lasso. It's called lasso regression. Basically, that's a penalty type being applied. So this is an L1 penalty. Ridge was an L2 penalty. Um, so the name for this is lasso. Very good. And for this one, I'm going to apply this elastic net regression. Elastic net means a mixture of ridge and lasso. So you see, I can even change the parameter value towards more lasso or ridge, between L1 and L2. I'll keep it at 50-50. Again, this is also another parameter value that you can experiment with, but, you know, um, I mean, um, I'll keep it just at 50-50, so like it's like half and half from both. Okay, rename this. This is called ElasticNet. Okay, let's correct that misspelling there. Good. All right, perfect. So now let's see the test and score metrics here, and each one of them should be kept here. Okay. Okay, they're very close to each other. They are very close to each other. Now, one thing I will do, well, first let's open that. So you see the R squared values, no regularization 0.87. Rich got a little bit better. ElasticNet got a bit better as well, but again, the values are so close to each other. So, yeah. Um, we're using cross validation. Let's make it tenfold cross validation. This is a small data set. Okay. Yeah, I mean, the difference between them is we can't say much really. They're almost the same, these outputs. Okay. So there's a table here. Table shows probabilities that the score for the model in the row, so in this row, is higher than that of the model in the column. Small numbers. Small numbers show the probability that the difference is negligible. Um, so coefficient is the coefficient of determination is the other name for R squared. Okay, so again, I could not really understand this. The table shows probabilities that the score for the model in the row in here is higher than that of the model in the column. Okay. Hmm. So here it's basically comparing the models, and yeah, Rich is a bit better than the one with no regression there that we can see right there. I mean no, not no. I mean no regularization. Yeah. Oh, okay. So you see these two values are adding up to 1. And here, yeah, these two will add up to 1. These two will add up to 1. So this is comparing linear regression lasso to no regularization. And here it's comparing this one, no regularization, to linear regression lasso. Okay, so basically, okay, I understand now. So the small numbers show that the probability that the difference is negligible. Okay. If there's a small value here, that difference is negligible. But for example, the 0.8 probability there is that the linear regression model, the rich model, is better than the no regularization version. Okay, so that's large there. So lasso is not good than any of them. You see these probabilities are very small, and you can see that from here as well. The R squared value is worst for lasso. Here, for example, ElasticNet is not that different from rich or no regularization, but it's better than the lasso model there. Rich is better than the no regularization because 0.8 probability it's better, and again 0.8 probability it's better than the linear regression lasso, and just a bit better maybe than the linear regression ElasticNet, but again it's 0.5, so there's not much difference there. Okay, so if it is more than 0.5 probability and closer to 1, that means that model is indeed better than the other one. There's more certainty there. That's what this is. So this is, yeah, this is a different way to look at this. But again, don't focus too much on this here. We can just compare these models by the R-squared value. Or you can use this RMSE as well. It doesn't matter. When you but either MSE, RMSE, MAE, MAPE, these are all error values. So the lower they are, the better. If they are zero, that's the best version. So the lower they are, the better. R squared is a score metric. So the higher, the better for R squared, right? So the closer to the one, the number one, R squared is, the better it is. Okay, again, errors, the closer to zero they are, better, because they should be lower, right? It's an error value. R squared is a score metric. So the higher it is, the better it is. Okay, one final thing, and I'm closing this regression. So here, there's some other models as well. Some of these machine learning models are good for classification only, some of them regression only, and some of them for both. So this linear regression is good for regression only. These some other models are good for both, and some of them are only for classification. Okay, for example, logistic regression. Although the name there is regression, this is only good for classification. Okay, you should not use this for regression. So here, this KNN, I'm just going to pull one of them. So KNN is basically k nearest neighbors. It looks at the k closest neighbors, and then basically it looks at the distance, and based on similarity, it will take the average based on the k closest neighbors. This k is something you decide on. So for example, here if you double click, you see there's 5 there, so this means it looks at the 5 closest neighbors. The distance metric is Euclidean, and the weight is uniform, so every point has an equal value. If you choose by distance here, that means the closer points have larger value. They have a larger weight in this calculation. But now it's uniform, so everyone is equal. So it looks at the 5 closest neighbors and takes the average of those 5. You can change this. You can make it 10, 15, 100, 50. You can make it 2. It's up to you. You can try different values. And that's something you should do. Just like I tried here different linear regression models, you can add more and more KNN models here. Change the K value in them. Maybe change the name of this node as well, of this widget as well, to reflect that. And then you can try a few. And then when you connect it to the same test and scores, you see I connected it to the same test and scores. It will be all shown here. So now I can compare all the models here. This is a very nice thing, by the way. So this KNN with 5 nearest neighbors is scoring 0.82. So this is much worse than these ones. But again, we should try different K values and see if they get better. Maybe 10 is better. Maybe just two value, K being 2 is better. Okay. So yeah, that's what you can do there. So that's this KNN model. There's a few other models. You can maybe try them out as well, but you might get an error because some of them is only for classification. Okay. So logistic regression is one of those, for example. But yeah, there's no harm in trying, so you can try different models there as well. All right, guys, that's it for regression. Thank you so much. Have a good day.